Blendoku? Blendoku. No, Blendoku. Blendoku, okay? So I shouldn't even write this down because it's like putting a bullet through your head. Blendoku. Don't even download it. It's insane. And I got last night, I'm like, okay, fine, I'm uninstalling it. I got up this morning, I'm like, oh, I installed it again. This is the stuff we're going to be talking about next few weeks. Okay, so how do we model this stuff? How do we model this stuff? Economists wrestled with how to model intertemporal choices for a long time because there's just an insane variety of different kinds of choices you might want to face. You might be faced with sort of like, well, would you rather, well, I'm not going to go into the crazy example. There's just a lot of complicated different choices that we're faced with. And we've got to find a way to simplify that so we can put it into a mathematical model. So we start with this. A basic sort of object of interest is referred to as a plan. Okay? Now, a plan may or may not actually involve you coming up with a detailed plan. A plan simply means an unfolding sequence of outcomes. Okay? So one unfolding sequence of outcomes might be I get 90% of my income, and when I retire I have a bunch of money. Another plan is I get 95% of my income, and when I retire I don't have as much money. Okay? So that's sort of a basic example of a plan. Another plan might be, I don't eat out. One of the things we're going to see in a little while is you get food stamps, and one plan would be I don't spend my food stamps. I spend my food stamps evenly over the course of the month, and another plan would be I splurge at the beginning of the month, and then I'm hungry at the end of the month. Okay. So then we define a sequence of time periods indicated by small t, 0, 1 up through capital T, and capital T could be infinity, and that just depends on how you're building your model. So essentially you could have today, tomorrow, et cetera, this year, next year, et cetera, and part of building a model is that you specify what the time period is. Okay. And then there's some outcome in each period, and we're gonna keep it really simple and just have one-dimensional outcomes. There's one thing you get. It could be an amount of money. It could be a certain quality of life, some numerical index of quality of life, right? So consumption, individual health status, something like that. Now, for simplicity, for the most part, when we're working with this model, we'll just put the x naught in dollar terms. But it could be anything. It could be x naught could be your entire consumption bundle at time t. So xt might be the whole array of apples, bananas, cherries, red cars, blue pencils, all those, and that's your outcome. So the x could be some huge vector of consumption, and then in each period, a plan would be your consumption of all different goods in each time period. For simplicity, we're going to keep it simple, and it'll usually be in dollar terms. Okay. So then plan P would be written this way. P is essentially sort of a vector over time of per period outcomes, and we will then come up with a utility function or an array of different utility functions with which to evaluate, with which to do utility maximization. Right. So we started by just imposing a bunch of structure on the kind of choices we're evaluating. So we found a way to sort of like define the elements of your choice set. Okay, so the three different retirement savings accounts were three different plans, and you could define them this way, and each one you have P1, P2, and P3, and those are now objects in your choice set. How do you choose things? You do it by utility maximization, so now we need to build a utility function. We'll do that on the next slide. So here's just a very simple example of how future outcomes are affected by current choices. Suppose we have a situation where one plan would be you save $5,000 a year for 4 years and have a great time in the 5th year, whereas another would be you just spend your entire earnings every year. So this is a setup, and you're going to do a little life on this in a second, where say your income is $15,000 a year, and one plan would be just to spend it every year, and another would be to save $5,000 a year. And if you look at these numbers here, what you'll see is that in this case, I've set it up so that saving $5,000 a year earns you an extra $10,000 in interest. So this is some kind of insanely profitable thing that you're investing in. And in the 5th year, you get all the payoff, and you have $45,000 to play around with. This is what I'm talking about, getting from some chaotic, complicated decision you've got to make, boiling it down into sort of numerical terms that we can work with. We have this idea that the further outcomes are in the future, the less we take them into account, typically. Okay, so which is this concept of discounting, and discounting is what we're going to be talking about for the next few weeks, right? So I'm going to come back to Alex, but the basic idea here is you're getting an extra $30,000 here, which is income of $10,000 plus you get your principal back. The question is having that extra $30K in year 5 actually worth giving up $5K a year for 4 years? And the answer is it's going to depend on how you feel about the future, because each of those first 4 years you're making a immediate cost delayed benefit choice, and the question is when you think about the benefit that you're going to get in the 5th year, how strongly do you take that into account? How much do you care about it? How much do you discount it? Okay, and that's what we're going to be exploring. Alex. I mean, so the question is, are the outcomes always consumption? So the annoying and precisely correct answer is that to an economist, everything is consumption, right? So at the moment, you're making a consumption choice, which is how much of your time, how much sitting in a chair listening to me do you choose to consume, right? Okay, is that, yeah. So I can frame everything as consumption. So the question is, how do we represent the preferences mathematically? How do we actually create a utility function? All right. So there are a few answers, and the first one is a combination of we do it this way and we do it badly. The standard model is called exponential discounting, also called the DU model. I don't know, it should be the ED model, right? But it's not. It's DU, which is for the discounted utility model. This was suggested in 1937 by Paul Samuelson, who is one of the sort of biggest names in all of neoclassical economics. Just knows that a hand up, or just you had to put it somewhere? Okay. And here's how it works. In each period, individuals will get what he referred to as instantaneous utility from the per period outcome in a plan. So the outcome is x naught, and the instantaneous utility, the utility that you get in period 0 from the outcome x naught in period 0 is u of x0, okay, and similarly all the way up. So this is a little bit like in a model of expected utility, right? If your house burns down, you're going to get a consumption outcome of a very low consumption outcome. What's the utility that you will get in that state of the world if that state of the world comes to pass? Similarly, what's the utility you'll get if your house doesn't burn down? And then we take a weighted average of those things. So this is a very similar setup where instead of different states of the world, we have different time periods. Fine. So this u dot, you know that if you have a function with just a dot in the parentheses, that dot just represents some set of arguments. Okay, so that's just a way of representing some arbitrary function. It's referred to as the instantaneous utility function. Matt Rabin refers to those as the little u's, because when you lump them all together, you're going to get a big u. So you'll hear me talking about the little u's, and I'm just talking about the instantaneous utility function. Okay, so consumers will value the plan in 2 stages, and this is going to be a lot like you're going to really see that this is very similar to expected utility. In expected utility, we do 2 stages. First, you evaluate how you would feel about each of the possible outcomes, and then you average across those. So we're going to do something very similar. The first stage is that we're going to discount we're going to come up with what the instantaneous utility is, and then we're going to discount that for each period by some factor d of t. t. So d is a discounting function, okay? And that's always going to be a number between 0 and 1. So essentially, it's like a percentage, right? So, well, you'll see what that looks like in a second. We're going to make the assumption that the amount the percentage weight you put on outcomes is going to go down over time. So the partial derivative of the discount function with respect to time is going to be negative. So what am I talking about here? Just to give you a very simple, basic example, what I'm talking about is, say, for example, if d1, right, that's the discount factor for the first period, next, the first period out in the future. If that was 1/2, what that would say is that you care 1/2 as much about sort of tomorrow or next year as you do about today. Okay? So if I say, would you like 1 lollipop today or 2 lollipops tomorrow? If D1, if your discount factor for tomorrow is 1/2, you'd say, I'm indifferent, right? Roughly, that's what that means. And then you sum all that up. You just say, I'm going to take the instantaneous utility for each time period. I'm going to discount it by some factor between 0 and 1, and that factor is gradually getting smaller over time, and then I'm going to sum them up. So the big U utility that you get from a plan P is simply equal to the sum from time 0, which is the present, out to whatever your sort of the end of your time horizon is, which again could be infinity, of the instantaneous utility of your outcome in that period, x of t, discounted by some number between 0 and 1. Okay, so at 0.9, you're saying that counts 90% of what it would count if it was today. So what does that look like? We have d of 0 times u of x0 plus d of 1 times u of x1, et cetera, et cetera. Blah, 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 right? Looks a lot like expected utility.
And d of 1 or d of something ever be greater than 1 because the data is either per day.
It could look like that. So I'm supposed to repeat the questions into the mic because of the webcast. So the question is, could d of some time period ever be greater than 1, like if you were looking forward to a birthday? We would think of that as a case of state-dependent preferences. Your preference for money is going to be higher on your birthday, or your preference for some outcome is going to be higher on your birthday, because your preferences will actually be different on your birthday. Typically not. That would be, as Matt Rabin would say, in the little u's, because your utility function may be different in different time periods. So we have this idea, for example, that, hey, when you retire, maybe you'll have learned to derive happiness from something other than money. Right? So if you don't save as much, that might not be because of discounting. It might be because you recognize that when you're old, you won't actually value money as much. That's in the little u's. Okay. And then you choose the plan that generates the highest discounted utility. So this is a trivial thing, but just to drive home the point over and over again, if you're doing economics, you're doing utility maximization. So you choose one plan over the other, if and only if when you stick that plan into the utility function, it comes out bigger. Okay? All right. So this is just exactly the kind of simplification that economists always do. Now, if you read the Frederick Lowenstein and Reed, I think, paper, it's a huge, long Journal of Economic Literature paper, in one of the sections you don't have to read, there's an enormous catalog of the assumptions that go into this. Right? So the fact that time periods are additively separable, basically that what I get tomorrow doesn't affect my utility today. I might care about tomorrow for its own sake, right? But one of the things that Lowenstein likes to say is, if you know that you're going out tomorrow night to an Italian restaurant, it is going to affect how you feel today about pasta. Right? Don't eat pasta today if you know you're going out to an Italian restaurant tomorrow. That's assumed away in this model. That cannot be represented in this model. There's all kinds of other of simplifications that are built into this that we tend to not pay very much attention to, and behavioral economists pay attention to all of them. We're going to focus almost exclusively on one subset of simplification, which is the assumptions that get made about this discounting function, this thing right here. Okay, did I skip a question? Yeah. So it looks like I'm making an assumption that the instantaneous utility function is the same over time. And that is, in fact, the assumption that is very frequently made. It's not required. You could have a little subscript or superscript that says, look, u superscript 1, u superscript 2, basically indicating that I think the actual shape of your preferences might actually change over time. That's fine. That's not a problem for this model whatsoever. Okay. Here's where things get out of control. Here's where things get crazy. So far, it just looks, all right, this is just the kind of dumb simplification that economists do. Here's where things get crazy. And in the sort of history of the philosophy of science, this should be one of the biggest case studies, because it's really crazy what happened. Remember, this is 1937. Samuelson made a very specific assumption about precisely how we discount the future. Okay? And what he said was the discount factor gets smaller exponentially over time, which means mathematically that this discount function d of t is simply delta to the t for some delta that is between 0 and 1. Okay? So, right, which that satisfies the condition that it should be decreasing over time, right? Because each period you're raising this number to a higher power, and you know that when you raise a number between 0 and 1 to a power, it gets smaller. All right, so this is exponential. So what does that look like? Here's d of t versus t. So we always make the assumption that d0 is 1. It's just a simplifying assumption without which it's a little tricky to make headway. So we'll assume that this is 1. Go away. And then d of 1, right, is going to be equal to just delta, whatever that is. And that's a parameter that we can either make up or go and measure somehow. And then it goes from there, right? So d2 is going to be equal to delta squared. And, right, so gradually the gaps here are getting smaller. And then d of 3, I don't know why I said 20 there too, d of 3 is going to be equal to delta cubed. And what you get, right, if you have 1, 2, 3, et cetera, is that this thing is convex, like that. Okay? Which means you get this lovely mathematical outcome, which is that you simply get to represent the utility function for a plan as delta to the t times u of xt. Okay? And now, if you were wondering this, now it becomes clear why we notate the present as t equals 0, because delta to the 0 is 1, and that's basically capturing the idea that we don't discount now. What we're talking about with the discounting function d of t is the percentage by which we deflate the utility of any future period relative to today. Okay? So we normalize d of 0 equals 1, and in the exponential function, delta to the t equals 0 gets you that normalization automatically. Okay? So the first period is just the undiscounted utility of x0, and then you get delta times the utility of x1, and then you get delta squared times the utility of x2, et cetera, et cetera. Okay? And it's lovely. And again, t could be infinity if you want, and it just all depends on how the math works out best. Okay? That's the model. Now, I thought I had some comments by Samuelson Well, hopefully they're in the next lecture. Let's do this. Let's just make sure that you guys can do the work. Whoops, that's not supposed to be there. Sorry, let me actually get this so that it's not there. There we go. Good. Okay. So suppose that we've defined delta equals 0.09, and we're making this wonderful simplification, which we will make over and over again. But the utility function, this is in dollar terms, and we're just going to say a util is worth $1. This is called the quasi-linearity assumption, right? If you've encountered that in your past studies. So basically, and this is another way of saying utility is measured in dollars. Okay. So making those mathematical assumptions, which of the following plans would have the higher utility and therefore be preferred? Go. Take a little time working groups. Right. So you're just applying this math. Sorry. You're just applying this math to those numbers. Couple more minutes. Questions? You got it. Okay. All right. So I'll open up the clicker thingy. Okay. Take about another 15, 20 seconds. I probably should have made this simple. I of course, had the advantage of using Excel. Okay, 5, 4, 3, 2, 1, and come on, there's 6 of you. Go. Click, click, click. No, okay, fine, left the room. Or fell asleep. All right, let me see how you did. All right. Which not, I didn't write down the answer. Yes, I did. Okay, A. So this is good. It turns out A is the answer, so congratulations to those of you who said A. And just quickly to go over the math, here's an Excel spreadsheet. You can get Excel to do this, and you should always use Excel to do this because it's really easy to do. Basically, what happens here is you write out a series of time periods starting with 0. You then plug in, somewhere up here, I've got a cell that says delta equals 0.9, and each of these cells is just this cell raised to the power of this cell, so it goes down over time, right? And then you just plug in the x's like this. You do the discounting, right? So this is 10 times 1, this is 10 times 0.9, this is 10 times 0.81, and you do it for each plan. You sum them up, and boom, there you go. Okay? So plan A with delta equals 0.9 gives you higher utility. You should save. Okay? What would you need to do to make plan B preferable? Add a year, make it take longer, so that basically by the time you get to the 45K, it's even further out and more discounted. What else could you do in this setup? So that's true. What if I leave the plans the same? Delta smaller. So what's going on here is that delta tells us how you feel about the future, and the smaller it is, the less you care. So here, this curve, whoops, where is it? Where'd it go? This curve, you can think of as diminishing marginal attention to the future, diminishing marginal interest in the future. There's one other thing that could represent. There's one other sort of material reason why you might put lower weight on the future over time. Can anyone think of what that would be? Uncertainty about what dimension of the future? Whether or not you'll be alive, right? So you could think about this as like a survival function. Well, every year there's a delta % probability that I'll be dead, and I certainly won't care about consumption if I'm dead. Which leads to all kinds of macabre ideas. Okay, let's get you out on the table a little bit. I haven't put the questions up here because there's 2 different versions of the handout. So there's group 1 and there's group 2, and in each of them you're faced with 2 plans, and the plans are extremely simple. A given quantity of money at a given point in time. Okay, so very quickly, just imagine that you were actually